Okay, so let's start then. Okay, so now I had to introduce proteins first because enzymes are proteins, and all the characteristics of proteins, um, particularly globular proteins, because that's what enzymes are, not fibrous proteins, but globular, and they are particularly sensitive to a number of things. Now, I don't know how much in 305 you guys talked about catalysts, but I want to talk about what a catalyst is. And an enzyme is an organic catalyst. Okay, so when we have a reaction, we start with reactants, and then assuming the products are more stable than the reactants, a reaction will happen, which means that the reactants, that means the reactants bonds are broken before they can form product. That requires energy, and that's what this here is. This bump, and this is potential energy. It's really Gibbs free energy, but which takes into account some other things besides just potential energy. But as far as our class is concerned, we're looking at potential energy versus reactants going to products. Okay, so there is a big step in the middle here. In this spot right here, it's called the activated complex. What that is, that's a mishmash of all the reactants atoms taken apart. And then because it's a high potential energy, we always want to have the lowest potential energy as possible. Um, then we're going to have two things happen. We're going to have reactants reformed and products formed. And that ratio is a constant ratio. It's called the equilibrium constant. And that determines how many products formed, how many reactants are reformed. Now, what a catalyst does is it lowers the activation energy so that less energy is required to start the reaction. And again, to start the reaction is we need to start breaking those reactant bonds. So if we looked at that reaction, we have hydrogen gas, oxygen gas yields water. Okay, so for the reaction to start, we put in activation energy. That takes the H to H bonds and the O to O bonds and breaks them. Okay, well, this is the activation energy here. So what happens is we have present. And then what's going to happen is we end up forming the product, which is waters. So these are new bonds now. We have H to oxygen bonds. Okay, however, this is, so after we inject activation energy, we break up the reactants bonds, forming, this is going to be the activated complex here. And then in the activated complex, we fall off on so this is reactants. And products. Okay, so this activation energy again determines how fast the reaction goes. The lower the activation energy, faster the reaction goes. Okay, so we have fast it goes and whether it's stable or not. We call that thermodynamically favored if the products are more stable than what you start with. That means the products have lower potential energy than the reactants. Okay, so in our body, we can't use the normal catalyst. We can working in a test tube on a bench top, which is usually something like platinum or magnesium or even concentrated acid. There's a lot of things that can be used as catalysts. Um, what our body uses instead are organic catalysts or enzymes, basically to do the same thing. They do magic things, actually. Okay, now enzymes are extremely specific, extremely specific. That's what makes them totally unique in the world, is that enzymes are so specific. They're also very fragile. So that's why our body goes to great lengths to make sure that the conditions that enzymes thrive in is maintained. That's things like temperature, um, solvent in our blood systems, pH of our systems, all this stuff comes into play as a which affects the efficiency of how an enzyme works. Okay, there are various classes of enzymes. Some are extremely extremely um, specific. Others are less specific. For example, urease only works on urea, nothing else. So if you want to do something else, you have a different substrate or a different enzyme. Also, the enzymes are very, very specific as to what they do. What I mean by that is they produce unique products. So you can have a number of enzymes work on urea, but if you wanted to convert it to ammonia and carbon dioxide, you have to use urease, nothing else. I'm going to stress this specificity. Okay, now, another important aspect of organic catalytic activity is it can be controlled or regulated, unlike a catalytic reaction in a test tube. That just goes, can't control it. Some of these are through feedback loops. In other words, for example, ATP is adenosine triphosphate. It's the energy molecule. Okay, so our body has a way to say, oh, we need more ATP, so we need to burn some more glucose. Well, what if we have enough ATP? Well, then the body regulates it by sending uh, things back that tone down the production of ATP through the glucose metabolism. And that's kind of the way enzyme activity works in our body, because we don't need everything all at once. And then, there's other factors that come into play. For example, starvation is different than non-starvation pathways, etc. Okay. Enzymes sometimes need a substance along with it. It's called a cofactor. Um, Cofactors can be a variety of things. They can be non-organic and organic. They're just basically the same thing. So you have an apoenzyme and a cofactor together forms the enzyme. So if you lose the cofactor, the enzyme um, becomes inactive and forms the apoenzyme. Um, Vitamins are frequently coenzymes. That's why they're important in our body. So we have a non-functioning enzyme plus the cofactor gives us an active enzyme. Okay, these are some examples of vitamins that are coenzymes, cofactors, I mean. Okay, now the magic happens in an enzyme at something called an active site. The active site is where the substrate, which is called in biochem language, a reactant is called a substrate. So when the substrate enters the active site, they form a complex which is the activated complex, and then products are formed. Now, again, notice this is a two-way street here. Because once the activated complex is formed, or the enzyme substrate complex is formed, excuse me, reactants will reform and products will form, depending on the stability of each. Okay, there are two very generic theories on active sites. One is called the lock and key theory. That means, like a lock, only one key will work. So that active site will only fit the substrate. Whatever that substrate is, it's got functional groups on it, etc. And then at the active site, which is right here, it's got functional groups in there that will take in the substrate and do the magic and produce the activated complex, and then the products are kicked out. plus the enzyme empty active site to be gone around again. Okay, so that's one very broad mechanism by which enzymes work with a substrate. There's also another theory it talked about, it's named the induced fit theory. That means the active site will actually change shape based on what the substrate is. So these are less specific. And we've talked about three enzymes in this class. And for example, amylase is the enzyme for carbohydrates. But within that, so that's general. So that is an induced fit. And we also have sucrase is this one up here, the lock and key, where it only works on sucrose. Now there's some other subtleties on this mechanism we're going to talk about. Something's called moderators. And moderators can change the shape of the active site to turn it on or turn it off. Okay. We mentioned kinetics at the first of this talk. And kinetics is how fast something will go. And that's, in biochemistry language, that's called enzyme activity. Talks about the rate, how fast the enzyme works, or how fast the reaction goes. Turnover number is related to this. Turnover is how many products are produced from the substrate. Okay. Let's see. That's all I wanted to say about rates. The rates vary horrendously. When you look at the difference between the turnover numbers between this guy and this guy. Here we have 36 million turnovers versus 900. Big difference. So it just depends on the complexity of the reaction that the enzyme is catalyzing, and also the regulation pathways that determine the speed at which that's supposed to happen. So it's kind of got a lot of variables in there that determine how fast the enzyme is going to work. Now, as far as catalysts in general, whether they're on the bench or in the organic body, we have the enzyme or catalyst concentration. We have the reactant or substrate concentration. And then we have the environment. And the environment, as far as enzymes are concerned, is water-based. But the water base is affected by the pH and temperature. Okay, so in other words, when enzyme concentration goes up, product goes up. When substrate concentration goes up, product goes up. Okay, now the problem is that's what this graph shows. So enzyme concentration goes up, rate goes up. But that doesn't go on forever. We plateau off here. In other words, with a given amount of enzyme, the enzyme can only do so much work because the amount of availability of active sites. The more active sites, the more work the enzyme can do. But if you have a fixed number of active sites, it doesn't matter how much substrate you throw in there, you can only do a certain amount of work. Kind of like life. Okay, so these are the factors that will affect, excuse me, affect enzyme activity. Temperature, pH. Solvent is always going to be water, so we're not going to change that, but that will affect the enzyme. pH, normally physiological pH is around 7. It's actually 7.4, except in certain areas of the body, like stomach, for example, where the pH is 2. And remember, pH is a measurement of acidity. And then physical movement. Basically, if we squash the enzyme, it'll stop working. And this all has to do with the shape of the active site. When you modify the active site shape, you modify its efficiency. You modify it a lot, the enzyme will not work. It won't catalyze anything. So we've got an optimum rate at a specific temperature. Going from one temperature to the other off of optimum will decrease the rate. Same with pH. Okay. So we're working with water in our bodies as a solvent. So that's not going to be changing. So you can see how various enzymes require different pHs. And this is, of course, at normal body temperature. Changes a lot. So if you, I mean, this is what you're looking at. The majority of enzymes are working in this area here. These are very alkaline conditions, very acidic conditions. Okay, so there are two kinds of things that will affect the enzyme activity. Inhibitors is one of them. Inhibitors decrease enzyme activity. So one inhibitor could be temperature, another could be pH, and the other could be a biochemical pathway. These would all inhibit the enzyme's efficiency or activity. Sometimes the inhibitors are irreversible. Enzymes can recover if the inhibitor is not too drastic. But if it's drastic, the enzyme is basically changed its shape so much that nothing happens. That's how a lot of poisons work. Antibiotics work if that way. If you're a bacteria, um, it will be irreversible. Heavy metals, cyanide. Cyanide works on the fourth stage of carbohydrate metabolism and the electron transport. It messes up that transport cycle, which is the most efficient part of the whole metabolism process, is the very last stage. Um, so these guys um, really do a job. Now, the reason why mercury and lead are here is because of one of the amino acids, cysteine, which is a thiol. Cysteine looks like this. What happens is lead gets in here, or mercury. And if that amino acid, this is cysteine now, that amino acid is part of an enzyme active site, then that active site will no longer work. Okay, and this cytochrome oxidase is located in the last step of cellular metabolism. That's what they used in um, um, the in Nazi Germany and at the concentration camps to kill people. They used a cyanide gas in the showers, quote unquote. They used cyanide. Also, they used that for legal death sentences for certain crimes. They used they put a bucket of water underneath the chair of the person being executed, and that's acidic, and they drop in sodium cyanide tablets, and the cyanide forms cyanic acid, HCN, and that's what kills everyone. Okay, we're going to talk about this cycle in a future presentation. Okay, now we talked about irreversible enzyme inhibition. There's also reversible inhibition. Okay, so um, if we, one type of inhibition is called competitive. In other words, if the inhibitor comes in and occupies the active site, that active site is no longer the same shape. So we start with this shape. And then once the inhibitor comes in, the shape looks like that. So now our substrate won't fit in because it requires that shape to fit in there. So that's a competitive inhibitor. This is done a lot in the body. Um, this substrate can be a receptor uh, where we have an inhibitor comes in and binds to that receptor, so the receptor doesn't function anymore as a neural receptor, and this is where neurotransmitters work a lot. If the substrate is a neurotransmitter and the active site is the receptor for that processing, we tie it up with something else, then that um, receptor cannot function as a receptor anymore. Okay, and sometimes the inhibitor can either bind inside the active site, like up here, or it can bind someplace else. And basically, again, here's the active site, and this is the changed active site. So the inhibitor binds someplace on the enzyme, and that interacts with the active site, changing its shape or function. And now the substrate can't get in there. Um, okay, allosteric regulation is similar to this, only it's more specific. So allosteric activity is monitored or um, activated by something called a modulator. That modulator can either slow up or increase the active site's efficiency. If it increases its efficiency, it's called an activator. Slows it down, it's called an inhibitor. So enzymes that work through modulator regulation have two active sites. They have a substrate active site. They have a modulator active site. So for example, if this is the okay, so the gray is the enzyme, okay, and this would be the moderator active site. This would be the substrate moderator site. Okay, so this particular, excuse me, this particular example, the active site shape uses V here. Okay, if this is the modulator here that comes in, once it's in here, it changes the shape of the active site. So this does not happen. And then the opposite can happen. In this case, when the modulator binds to the modulator active site, well, at this point, this doesn't happen because the site is a different shape. Once the modulator binds to the active site, it changes the shape to the correct shape for the active site, so then the substrate can fit in. So this would be um, uh, where the activity is increased. So allosteric regulation is where a modulator comes and binds to the modulator active site and either changes the active site to so the substrate fits in, which increases the activity, or modifies it so the substrate doesn't fit in there, which inhibits the reaction. Okay. Okay. Sometimes during these pathways and when organic pathways in our body, the regulation is done by it's called enzyme induction, where our body will actually synthesize the enzyme that it needs for something to happen. So enzyme regulation, extremely important process in our body. Okay. Um, Things can be inhibited both reversibly and irreversibly. If it's reversible, then we have what's going on is the inhibitor is done allosterically, or it works directly on the active site. And both those processes are reversible. Okay, so that's enzymes. So allosteric regulation, very important. Um, Both increasing the activity and inhibiting. Oops. This would be inhibition here. This would be activation here. Um, so we can modify the shape of the active site by having an inhibitor occupy the site so the substrate can't get in. And then we can irreversibly modify the enzyme by modifying the amino acid in the enzyme um, 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 sequence. We can either change the enzyme by changing the amino acid, modifying the amino acid, deleting it, or adding to it. All those will change the shape of the active site, meaning the enzyme will no longer function catalytically. Okay, so that's it on enzymes. What I want to do is go over something called, are there any questions about kind of enzymes? And remember, enzymes are globular proteins. So anything that will affect the shape of a globular protein will affect the enzyme because it's going to affect the shape of the active site on the enzyme. Now, the enzyme active site is a small part of the whole makeup of the enzyme, but it's the crucial part that actually catalyzes the reaction. So that's why you always say it modifies the shape of the active site. Okay. Okay, I want to cover one more thing today, and that's enzyme classification. Um, Enzymes usually end in ASE, except old ones that did not adopt the ASE. Trypsin, pepsin are examples. Typically, though, they have two parts. They have a substrate part and also the enzyme class that describes the reaction they're catalyzing. So, for example, in this example here, we have glucose going to, this here is 6-phosphoglucose. And what's happening is we're having a ester, phosphate ester formed there. And this would be actually the first step of glycolysis, which we phosphorylate glucose. So the name of the enzyme that catalyzes this is glucose is the substrate, and the reaction process is called kinase. So we look at all of these. This will talk about the different kinds of processes that enzymes do. And this is the processes here. So there's hydrolysis, transfer of functional groups. In other words, moving one functional group to another. Okay, a kinase is going to take a phosphorus group and move it between substrates. So all the kinases are involved in making ATP, ADP, AMP, glycolysis. We're talking about phosphorylation of glucose. Anyway, those are all kinases. Now, when we get into the nitty-gritty of all these processes, I'm not going to focus on the real names of the enzymes. I'm going to focus on this process here, where you name the substrate, and then you name the processes that the enzyme is doing. Is it transferring a functional group? Is it doing hydrolysis? Is it isomerization? There's a lot of isomerases during our metabolism. And so that's what I'm going to be focusing on. So we'll have some questions on your final regarding the process. And I would, for example, I would give this as an example. That would be then glucose kinase. Okay. And then this is the process here. It's always in two parts. Substrate, and not the final product, the substrate, what are we starting with? So we're starting with glucose. We're transferring a phosphate group from another phosphate substrate over to here. Okay, so this goes through and talks about what they all do. And now for your final, it's going to be open book, open notes. Really, it's open notes. You will not be allowed to use your phone, so bring whatever you want in. And remember, these slides are located in so this is going to be the slides that I use during the lectures. Okay, so are there any questions about what we talked about today?